Assalamu alaikum class. Today we will start lecture number 15 in which we will read conductors, and after that we will also learn about its basic properties, and after that we will move on to discharges, surface charges and force on a conductor, and last one is capacitors. Now in this slide we will see what are conductors. As we have already studied in FSC, we have three types of material: conductors, second one is insulator, and third one is semiconductors. Now you will read conductors. Conductor is a type of material that allows the flow of charge in one or more directions. Materials made of metal are common electrical conductors like silver, gold, and copper. In simple meaning, the materials having large number of free electrons and conduct current due to potential difference are called conductors. There are properties of conductor. First one is there is no electric field inside the conductor. If you try to make field inside, the charges in conductor move around in such a way as to cancel your attempt. And del U is equal to integral of E dot dl, as we studied in first line, is equal to 0. So del U is equal to 0. The second one is potential difference between 2 points is 0. Third one, the charges can exist only on the surface of conductor. The inside is neutral. There are equal number of neutrons and protons everywhere, otherwise there would be electric field inside. Now we will read basic properties of conductor. First one is conductive property. Inside the material of a conductor at equilibrium, the electric field is always 0. Inside the material of conductor at equilibrium, the potential difference between any 2 points is 0. Explanation is given here. Conductor is placed on in an external electric field. Consider a plate having positive charge. It creates electric field. As we know, when two plates of opposite charges or same charges are placed, then there develop a electric field. The direction of electric field is always from positive to negative charges. So in this case, when we consider a conductor having positive and negative charges inside, an electric field creates, and its direction is always from positive to negative. So the net charge density in the interior of the conductor is always 0, because inside the material of conductor electric field is 0. Because of this, inside the material of conductor electric field is 0. So in case when we are considering conductor having positive and negative charges inside, then electric field creates, and its direction, as we know, always from positive to negative. If we place a conductor in a space in which electric field exists, that means we are considering a conductor in an external electric field, and the net charge on the conductor is 0, because in start number of electrons and protons are equal, so net charge on conductor is 0. But when we apply electric field on the conductor, across the conductor, then electrons begins to move opposite to the surface of conductor and holes create, means positive region create inside the conductor, and these positive charges begins to move on the surface. These charges on the surface produce their own electric field, whose direction is from positive to negative, so they both cancel out each other, then net electric field inside conductor becomes 0. So we can clearly see that net electric field inside the conductor becomes zero from the figure. Now, in this slide, we will talk about net charge resides on the surface of conductor. The net charge of conductor resides entirely on its surface. The mutual repulsion of like charges from Coulomb law demands that charges be as far apart as possible and on the surface of the conductor. The electric field inside conductor is zero. Outside the conductor, the field is not zero. For here, external electric field and inside electric field do not tend to cancel. Remember that. Inertia of charge can have no electric charge in static situation. For example, draw a Gaussian surface and electric field is zero inside the conductor. As we know, flux is equal to E dot dA, where inside the conductor electric field is zero and flux is also become also zero. So phi is equal to 0. So in this slide, as we know that flux is equal to charge over epsilon, that is not exist in conductor because we considering charge is equal to 0. Equipotential. What is the concept of equipotential in conductors? We assume electric potential is same at every surface. If potential is not same, then charges move and they move in potential difference. It means positive move from high to low and negative always move from low to high. So when the charge move in a conductor, it dissipates energy, but it is not a possible always. When it acts as equipotential, it is for a very short time, but it happens that surface of conductor is equipotential, and we have to prove also inside of conductor is equipotential. Means that in conductors equipotential means potential is same at every surface. So we can say conductor is equipotential, and we know V potential is given by VB at 2 points. Means for if A and B are any 2 points within or at the surface of a given conductor, means A and B are 2 points at or within the surface of the conductor. Then the potential at potential difference between these 2 points VB minus VA is equal to integral E dot dl is equal to 0, because A is equal to 0. So from formula we know that F is equal to QE as Q is equal to 0. So that's why F is equal to 0. We are considering E is equal to 0. So from this equation, VB is equal to VBA. What is induced charge? In simple words, from figure we can say that if we hold a charge plus Q near an uncharged conductor, means a neutral conductor, the two will attract one another. The reason for this is that Q will pull minus charges over to the near side and repel plus charges to far side. Since the negative induced charge is closer to Q, there is a net force of attraction. So the presence of a charge object near neutral conductor will force electrons within conductors to move. The flow of electrons result in permanent charge being left upon the object. That is called induced charge. Next is surface charges and force on a conductor. When an electric field is applied to the conductor, free charges inside the conductor move until the field is perpendicular to the surface. The parallel component exerts force on free charge, which moves the charge until force is equal to 0. Now we will read surface charges and force on conductor. Some charges repel each other. Like charges, for example, positive charge repel positive charges, and positive charge attract negative charges. Means to say that always repulsion occur between like charges and attraction occur between opposite charges. So consider a spherical conductor having charge q and surface charge density sigma. Then this charge resides on surface of conductor. Now if we match both situations, then it is clear that all charges repel each other and force exerted on it. This is directed outward. Then in this spherical body there exists a pressure. In simple words, means to say that if we consider two like charges, there is repulsion occur, and if we consider two unlike charges, then there is attraction occur. But if we consider a spherical conductor and having charges having positive charges on its surface, then we can clearly see that like charges always repel. So the direction of repulsion is outward, and there exists a pressure. The question arises, why net charge reside on the surface of conductor? The reason is that since the electric field is zero inside the conductor, as the charge is equal to 0, the mutual repulsion of like charges from Coulomb's law. Coulomb's law, which is given by F is equal to K Q1 Q2 over R square, that demands that charges be as far apart as possible, and means that the distance between charges is greater. Hence, on the surface of conductor, the net electric charge of conductor reside entirely on its surface. That's why charge resides on the surface of the conductor. So in previous slides we discussed about electric field inside and outside the conductor, as electric field inside the conductor is 0 and outside the conductor is not 0. Inside the conductor, electric field is 0, but at the surface there is electric field whose magnitude can be given as E is equal to sigma over epsilon. N is the unit vector that is directed outward. If we know about electric field E and charge density, then we calculate force on the conductor, that is F is equal to QV, and similarly pressure, that is equal to P is equal to F over A. But there is discontinuity in the field E. So at the surface of conductor there is discontinuity. We don't know which electric field exert force on the surface. Now to resolve this, we consider three close points. If we introduce a surface, then it modifies electric field on the upper and lower part. We know if in a charge electric field normal to charge whose magnitude is E is equal to sigma over 2 epsilon. Means to say that in the presence of electric field, a surface charge will experience a force per unit area, F is equal to sigma E. But there is a problem here. For electric field that is continuous at the surface charge, so we are supposed to use E electric field above and electric field below, or some other magnitude same, but but there are opposite directions of these electric field. In this slide, let's focus our attention on a tiny patch of surface that we can clearly see from figure. Patch of surface. Make it small enough so it is essentially flat and the surface charge on it is essentially constant. And the total field consists of two parts, above and electric field above and electric field below. So it is given by the equation E above is equal to E other plus ES. E below is given by E other minus ES. The patch of surface is given, and on this path the force is given by the electric field exists already. So electric field can be given by E is equal to, that is average is given by E below plus E above over 2. So in simple way it can be written by this equation: E is equal to 1 over 2 bracket E above plus E below. As we consider the conductor in an electric field, so the force experienced by the conductor is given by equation F is equal to QE. Take the derivative of this force, dF is equal to, put the value of E sigma over 2E, 2 epsilon dot, and value of Q here sigma dA. And then for small patch, dF is equal to sigma square over 2 epsilon dA, and here we can get F is sigma square over 2 epsilon, and that is unit vector pointing outward. Pressure, similarly, P is equal to dF over dA. Put values and solve it by simplifying. Sigma square over 2 epsilon dA divided by dA is equal to sigma square over 2 epsilon. As we know that E is equal to sigma over epsilon. Then pressure, we can calculate P is equal to sigma over 2 epsilon dot sigma is equal sigma over 2 dot sigma over epsilon is equal to sigma over 2 dot electric field E. P is equal to sigma square over 2 epsilon is equal to epsilon over 2 dot sigma ka square over 2 over epsilon square over 2 is equal epsilon over 2 dot electric field square. Now we will talk about capacitor. What is capacitor? Capacitor is a device that is used to store electric charge. The effect of capacitor is called capacitance. Q, that is charge proportional to the V, that is potential difference. Q is equal to CV. C is proportionality constant because Q is proportional to V, and when we write in simple form, Q is equal to CV and C is the proportionality constant. Here we can get C is equal to Q over V, that is capacitance. The capacitance is defined as the capacitance of capacitor is 1 farad if a charge of 1 coulomb given to one of plate of parallel plate capacitor produces potential difference of 1 volt between them. So the SI unit of capacitance is 1 farad. Now mathematically explanation is given in this slide. Consider a parallel plate capacitor. It is experimentally observed that With more charging voltage, the electric field between plates is stronger, hence more charge is stored. From figure we can see that a parallel plate capacitor and which is connected to a battery means voltage is applied to this parallel plate capacitor, and it is observed that experimentally observed that with more charging voltage the electric field between plate is stronger and hence more charge is stored, and the amount of charge stored in capacitor is directly proportional to the potential difference of battery, which is written as Q is equal to CV. C here is given by C is equal to Q over V, as we know that C is proportionality constant and it is called capacitance of capacitor. So capacitance does not depend on charge and potential difference. As a unit of capacitance is farad, this unit is named in honor of Michael Faraday, who developed the concept of capacitance. The submultiples of farad is microfarad and picofarad are more convenient unit in practice. Capacitance is purely geometrical quantity determined by size, shapes, and separation of two conductors. In SI units, C is measured in farad. Farad is coulomb per volt because C is equal to Q over V and farad become equal to coulomb per volt. The factors which affect the capacitance. The factors that affect the capacitance are area of plate, separation between plates, the electric medium. These are the factors which affect the capacitance of a capacitor. Now there are some problems and examples related to our lecture. Problem number 2.41, which is mentioned here. Two large metal plates, each of area A, are held a small distance d apart. Suppose we put charge Q on each plate. What is the electrostatic pressure on the plates? We have to find the electrostatic pressure on the plates. So consider two large metal plates, each having charge Q. So as we know, the electric field creates and its direction is always from positive to negative, and these two large metal plates are separated by distance d. Now the electric field between the plates is equal to 0, but there is electric field outside the plates which is given by sigma over epsilon naught. But as we know, the surface charge density is equal to charge over area. So we put the value of sigma in electric field and we get E is equal to charge over epsilon naught area, epsilon naught times area. We know the pressure is equal to epsilon naught E square over 2. Here we put the value of electric field which is given by Q over epsilon naught times A. After putting the value of electric field, we get pressure equal to Q square over 2 epsilon naught A square. Now next problem 2.43, which is taken from David Griffith book Introduction to Electrodynamics, which is given here. Find the capacitance per unit length of two coaxial metal cylindrical tubes of radii A and B. So here we have to find the capacitance of two coaxial metal cylindrical tubes having radii A and B. From figure we can see that there are two coaxial metal cylindrical tubes. Inner tube having area A and outer tube having area B. And length of the cylindrical tubes is H or L. So as we know that capacitance is equal to charge over potential difference. So for finding value of V, we first need to find value of electric field. So we first solve for E. E is the electric field. So let charge Q enclosed by Gaussian surface. We imagine a Gaussian surface around the tubes and calculate the value of electric field. And electric field is given by Gauss law is equal to closed integral E dot dA is equal to Q over epsilon naught. But the value of area of cylinder is 2 pi r h. So put the value of area here. E 2 pi r h is equal Q enclosed over epsilon naught. Take the value of electric field from here. E is equal to Q enclosed over epsilon naught 2 pi r h. Now the potential between two coaxial metal cylindrical tubes is given here. V is equal to minus integral limits are a from a to b. E dot dl is equal to integral q. Put the value of e here. Q enclosed over E naught 2 pi r h dr. So we take the integral of 1 over r dr, which is equal to ln over a over b. After putting the limits value, integral value ln a over b, and as we know that capacitance is equal to q over v. Here we put the value of v and calculate our answer. C is equal to q over v is equal to minus 2 pi epsilon naught h ln b over a. As in the question, we have to answer capacitance per unit length. So C over L, C over H is equal to 2 pi epsilon naught ln b over a is our answer. Next is an example 2.12 about capacitance. Find the capacitance of two concentric spherical metal shells with radii A and B. We have two concentric spherical metal shells having radii A and B, and we have to find capacitance of these spherical metal shells. Let place charge plus Q on inner sphere and minus Q on outer one. The field between sphere, the field creates is given by E is equal to 1 over 4 pi epsilon naught Q over R square, and R is a unit vector pointing outward. And the potential difference between them is V is equal to minus integral B to A. E dot dl is equal to, put the value of E here, minus q over 4 pi epsilon naught integral b to a and 1 over r square dr. We have to integrate with respect to r, and after integrating 1 over r square dr and putting limits of integral, we will get q over 4 pi epsilon naught 1 over a minus 1 over b. This is the value of potential difference between the concentric spherical metal shells. And after that, we need to find capacitance, which is equal to C is equal to Q over V. Here we put the value of V and find the capacitance. As we know, charge is proportional to potential difference. So the capacitance is written as Q is directly proportional to V. Q is equal to CV. C is the proportionality constant. We put the value of V here and get the value of capacitance, which is given as C is equal to 4 pi epsilon naught AB over D minus A, which is the capacitance of two concentric spherical metal shells with radii A and B. Next is also an example 2.11. Find capacitance of a parallel plate capacitor consisting of two metal surfaces of area A held a distance d apart. In the previous example, we find the capacitance of concentric spherical metal shells. Now here we have to find the capacitance of parallel plate capacitor. So from diagram we can see that parallel plate capacitor consisting of two metal surfaces of area A held a distance d apart. If we put plus q on the top and negative q on the bottom, they will spread out uniformly over two surfaces provided area is reasonably large and separation small. The surface charge density, as we know, equal to charge over area on the top plate, and the field is given by E is equal to Q over epsilon A. It's is given here. The potential difference between plates is therefore V is equal to Q over A epsilon naught D, and the capacitance is given here. C is equal to Q over V. Here we put the value of potential difference, which is QD over A epsilon naught, and after simplifying we get the capacitance of parallel plate capacitor, which is mentioned here. C is equal to A epsilon naught D. For example, if plates are square with sides 1 centimeter long and they held 1 millimeter apart, then capacitance C is equal to 9 multiplied 10 to the raised by minus 13 farad. If we put here values of area, epsilon naught and distance, which is given here in example, we can get the value of capacitance C is equal to 9 multiplied 10 to raised by minus 13 farad. Next, problem 2.39. Two spherical cavities of radii A and B are hollowed out from the interior of a neutral conducting sphere of radius r, as shown in figure. At center of each cavity, a point charge is placed call these charges QA and QB. So as shown in figure, we can see that there are two cavities of radii A and B. So first we have to find surface charge densities of all these cavities, sigma A, sigma B and sigma R. So surface area for inner cavity A is equal to sigma A is equal to minus QA over 4 pi A square. And because the induced charges due to charge QA, we have negative sign minus QA, and A is the radii of this cavity, so that's why we put A here, A square. Similarly for cavity sigma, surface area for second inner cavity, sigma B is equal to minus QB over 4 pi B square. B is the radii of this cavity, so we put here B square. And for sigma R, which is a total charge of sphere of radius R, is equal to QA plus QB over 4 pi R square. R square is the radius of conducting sphere. This is all about first point, which is find the surface charge densities. Now in second part we have to find what is the field outside the conductor. We have to find the field outside the conductor. For finding field outside the conductor, we have to imagine a Gaussian surface around the conductor. So imaginary Gaussian surface is shown in figure, and the charge enclosed by the Gaussian surface is QA and QB. So from Gauss's law we can write total charge QA plus QB over epsilon and is equal to E integral dA, and area of sphere is equal to 4 pi R square. After putting the value of area, we can find the value of electric field from here. E is equal to QA plus QB over 4 pi R square epsilon naught, and with the unit vector R. This unit vector is directionally outward. Now we have to find in third part is what is the field within each cavity. For finding the each field within each cavity, we again consider Gaussian surface around each cavity. So for cavity A and cavity B, for cavity A, Gauss's law is written as Q enclosed over epsilon naught is equal to enclosed integral E dot dA. And area of this cavity having area having radii A 4 pi R square RA square. So after simplifying we get the electric field within each cavity, and RA is the unit vector for the cavity having radius A. This shows the direction of the electric field. Similarly, electric field within cavity B, EB is equal to qb over 4 pi rb square epsilon naught. Now problem 2.3a. A metal sphere of radius r carrying charge q is surrounded by a thick concentric metal shell, inner radius a, outer radius b, as shown in figure. The shell carries no net charge. In first part, we have to find surface charge densities sigma at r, at a, and at b. In previous problem, we find surface charge densities. In similar way, in this problem we find the surface charge densities. First, we have a sphere whose radius r. So, for this sphere of radius r, we have surface charge density is equal to q over 4 pi r square, capital R square. And for inner sphere, sigma a, for inner sphere whose radius is a, sigma a is equal to minus q over 4 pi a square. A is the radius of this small sphere. For outer surface, which is having radius b, sigma b is equal to a q over 4 pi b square. B square is the radius of this sphere, this outer surface. Now in the B part, find the potential at center using infinity as the reference point. As we are finding the potential, so potential is equal to integral limits are infinity to r kq over r square dr. After breaking limits, minus integral limits are infinity to b kq over r square dr minus integral limit a to r kq over r square dr. And after simplifying, minus kq minus 1 over r is after integrating limits, and after putting limits we get minus kq 1 over infinity minus 1 over b plus 1 over a minus 1 over r. 1 over infinity goes to 0, so we get v is equal to kq 1 over r plus 1 over b minus 1 over a. This is all about potential at the center. After simplifying, we get the potential of this form. Now in third part, see, now after surface is touched to a grounding wire, which drains off charge and lower its potential to 0, how do you answer to A and B change? Now from figure we can see that outer surface is touched to a grounding wire. Outer surface is touched to grounding wire. So what is the answers after outer surface is touched to grounding wire? A and B tells about A and B. For part A, charge in sigma A remains unchanged. There is no effect on this surface, but for part B, charge in sigma B is 0. So there is a changing happen in B part, which is given by V is equal to kq 1 over r minus 1 over b.